Welcome you all once again for my series of video lectures. Today, I'm going to discuss about a concept called digital logic circuits. Basically, there are two types of digital logic circuits we have. One is a combinational logic circuits and second one is sequential logic circuits. For this class, I'm going to discuss about some of the combinational logic circuits like adder, subtractor, a circuit which can do both addition as well as subtract. So, introduction to digital logic circuits. There are two types of digital logic circuit. Just now I told to you. One variety of digital logic circuits are combinational logic circuits. The examples of combinational logic circuits are adders, subtractors, decoders, encoders, multiplexers, demultiplexers, comparators, code converters, and etc. Similarly, the second variety of digital logic circuits are sequential logic circuits. Some of the examples for sequential logic circuits are memory elements, latches, flip-flops, registers, and counters. Into combinational logic circuit. What a combinational logic circuit is? A combinational logic circuit whose output is always dependent on the present input combinations. See here, friends, this is a combinational logic circuit. It has m number of outputs with n number of inputs. Always these outputs are depends on the present input combinations available on this n inputs. So that these circuits we call as combinational logic circuit. That means the output of the circuit is completely depends on the combinations present over the inputs. Second one is a sequential logic circuit. A sequential logic circuit whose output is always depends on the present inputs and past history of the circuit. The past history of the circuit means what is the past output of a circuit, and that output of the circuit is depends on past inputs. This past history of the circuit can be stored in a memory elements. See here, friends, this is a sequential logic circuit. It is a combination of combinational logic circuit and a memory element. Basically, this is a memory element which is useful for us to hold the past history of the circuit, so that the output of this circuit is not only depends on the present input, it is also depends on the past history of the circuit, which is provided by memory element. So that we can conclude that a sequential logic circuit is a combination of a combinational logic circuit and a memory element. Now, we'll go and see how to design a combinational logic circuit. If I want to design a combinational logic circuit, I should follow a fixed procedure. It consists of different steps. In that, my first step is from the specifications of the circuit, determine the required number of inputs, outputs, and assign the symbols to each and every input as well as output of our circuit. I repeat once again, if I want to design a combinational logic circuit, what I have to do is, first I have to go and represent in bar diagram representation. In the process, based on the specifications of the circuit, I should know how many number of inputs the circuit has and how many number of outputs that circuit has. And that inputs and outputs, we should assign the symbols. The second thing is, after getting the block diagram, the second thing is we have to go and derive the truth table of the logic circuit. What a truth table gives for us? The truth table gives the information of digital logic circuit, how the output varies with respect to all possible input combinations. So we have to go and get the truth table. That should be the second step. Coming to the third step is, once we are getting the truth table of digital logic circuit, we have to go and get the simplified Boolean expressions by writing of Boolean expressions first from the truth table, later with the help of simplification methods, either applying of Boolean algebra theorems, properties, laws, or by using of K-map, or by using a tabulation method, we have to simplify it, and we are getting a simplified expression. That should be third step. And coming to the last step, what are the simplified expressions we are getting at the end? With the help of that, we should go and realize it with the help of logic circuits, that digital logic circuit. So these are the 4-step procedure for making of any digital logic circuit. Once again, I quickly repeat the design procedure of combinational logic circuit. Number 1 is we have to find how many number of inputs and outputs are needed for the required combinational logic circuit. Based on the specifications, we have to give the symbols for each and every input as well as output. Number 2 is deriving the truth table. Number 3 is go and write output expression by the combination of input variables. And after that, you should simplify it by using any simplification method. At the end, the simplified expression can be designed with logic gates. So this is a 4-step procedure for designing of a combinational logic circuit. For example, I start my discussion with how to make an half adder is. Half adder is a combinational logic circuit. It can add 2 bits at a time, and it can produce sum and carry are the outputs. If you're coming to the block diagram representation of it, so here if you observe this is a half adder with an inputs x and y, and outputs are sum s as well as carry c. So here I need 2 inputs as well as 2 outputs. So just now we've gone through the design procedure of combinational logic circuit. As a first step, what we do is we should identify how many number of inputs as well as outputs for a circuit, and we should assign the symbols to the input as well as output. That I was doing here. Later, the second one is making a truth table of it. So I have 2 inputs. The possible combinations are 4. We know that by using 2 variables, we are going to get 2 power 2 combinations, that is equal to 4 combinations. Those are 0, 0, 0, 1, 1, 0, and 1. What this half adder can do? It do addition between the inputs. So 0 plus 0 is 0, and we didn't get a carry. So carry also 0. Next 0 plus 1 is 1. Again, we are not getting a carry. So carry is 0. Next is 1, 0, sum is 1. And again, we are not getting carry. So carry is 0. 1 plus 1, sum 0, and carry is 1. So this is the truth table. Now coming to the output functions of sum as well as carry. Once you observe only x, y, and sum, these are 3 columns, it is very clear it is equivalent to 2 input exclusive OR gate. So that for that case, output is x is exclusive ORing with the y. We can also written as it is x bar y plus x y bar. So this is that output expression for sum is. Similarly, if you observe x, y along with the carry output, its truth table is just equivalent to AND gate truth table. So here AND gate output, we know that output is A dot B. So here the inputs are x and y, so that output of my AND gate is x dot y. So here C is equal to xy. Then implementation of it by using a logic gates. Here I need an AND gate along with a NOT gate, and here also I need an AND gate along with a NOT gate and an OR gate. This is that simplified structure for sum output is, and a carry output is simply an AND gate. So this is. We can also replace this with an exclusive OR gate. So this is that, and this is an AND gate. So here we are getting a sum output, and here we are getting carry output. So sum is equal to x is exclusive ORing with a y, and carry is xy. Next one is a full adder. What a full adder is? Again, it is a combinational logic circuit. It can add 3 binary bits at a time, and it produces sum and carry are the outputs. In previous case, half adder can only do addition between 2 inputs, but now the full adder can do addition between 3 bits. Here x, y, and z are the 3 inputs, and it will produce sum and carry. So here also in a block diagram representation, according to the functionality of full adder, I need 3 inputs. Those are x, y, z. These are the variables or symbols I assign to my the inputs. And here there are 2 outputs. One is sum and carry. Here I was applying the symbols for sum output is and carry output is C. Coming to the truth table of full adder is, by using 3 variables, we are getting 8 different combinations. That is 000, 001, 010, 011, 100, 101, 110, and 111. Now, if you add these 3 bits, 0 plus 0 plus 0, 0, carry 1, 0 plus 0 plus 1. So only 1 was present. So sum is 1, carry is 0. 0 plus 1 plus 0, again only one input was 1, so that sum is 1, carry is 0. Next, 0 plus 1 plus 1, here there are 2 ones, so sum 0, carry 1. Again 1 plus 0 plus 0, sum is 1, carry 0. 1 plus 0 plus 1, again here also there are 2 ones, so sum 0, carry 1. 1 1 0, again 2 ones, sum 0, carry 1. Here there are 3 ones, sum 1, carry 1. So what should be the output expressions for sum and carry? If you consider min terms notation, so sum is 1 for this combination. This combination min term is x bar, y bar, z. Or in a shortcut, we written as small m1. And here again, sum value is 1. For that case, x value 0, y value 1, z equal to 0. Then your min term is x bar, y, z bar. In m notation, it is called as m2. And again, sum is 1 for 1 double 0, that is x1, y0, z0. And for this case, your min term is x, y bar, z bar. And last case is here also sum is 1. So it is 1, 1, 1 case. Your min term is x, y, z. And which equivalent in m notation is m7. So I written as sum is equal to sigma m of 1, 2, 4, 7. In a similar way, the carry is 1 for 0, 1, 1. So your min term is x bar by z, which is equivalent to m3. And next, it is 101, which is equal to x, y bar, z. And it is equal to m5. And next one is 110. It is x, y, z bar, which is equal to m6. 111, it is x, y, z, which is equal to m7. So my carry output C is equal to sigma m of 3, 5, 6, 7. If you simplify this, then we are getting these expressions. So unfortunately, the sum we are not simplified here. Okay, then what we have to do? See here, friends. If I use a K-map simplifications, the sum cases, sum is 1 for 1, 1 for 2, 1 for 4, and 1 for 5. All these are the isolated. So that here I'm going to use Boolean algebra theorems as well as a properties. This is my expressions. So to simplify in this order, at the end, I was getting exclusive OR operation between all my 3 inputs. But coming to the carry case, carry is 1 for 3, 5, 6, and 7. Here the possibility for getting of 3 pairs. So for this pair, the value is yz. For this pair, it is xz. And for this pair, x, y. So here, this is your simplified expression is. Okay, so this is a logic diagram for getting of this. xy, xz, yz. All are ORing together. So sum output is. So this is the logic diagram for our full adder circuit. So this circuit also we can replace with 3 input XOR gate because sum output is Z is exclusive ORing with, X is exclusive ORing with Y, so that instead of this whole circuit, we'll go and use simply a 3 input exclusive OR gate. Then coming to another important one, that is how we are implementing a full adder by using 2 half adders and an OR gate. See here, friends, this is 1 half adder. We know that, and a half adder output is X is exclusive ORing with Y. Once we have X and Y are the input, and carry output is simply XY. And similar structure, I will go and take one more half adder circuit is. For the second half adder circuit, the inputs are the first half adder sum output as well as the third input. The third input as well as first half adder sum output. So this is a given to the input of second half adder is. In that process, again in a second half adder, again we have an exclusive OR gate as well as an AND gate. What is an output of this exclusive OR gate is, this input is X is exclusive ORing with the Y, and it is XORing with the third input, that is Z. So that the output of this exclusive OR gate is X is exclusive ORing with the Y, is exclusive ORing with the Z, which is sum output. Just now we have gone through that full adder circuit. Sum output is exclusive OR operation between all our three inputs. Then coming to carry case. So carry was produced by an AND gate. For this AND gate, one input is sum output of first half adder, that is X is exclusive ORing with Y. And the second input is nothing but our third input, that is Z. Then the output of this AND gate is X is exclusive ORing with Y is a multiplying or dot with Z. So this is a one input is given to an OR gate, and here also half adder 1 carry output is there. Both are given to an OR gate. This OR gate will produce a final carry output. What is this is? So one input of this OR gate is XY, and another input is X is exclusive ORing with the Y dot Z. So this is a simple full adder implementation by using two half adders and an OR gate. And the next one is another adder that is called parallel adder. This parallel adder we can also call a ripple carry adder. What this parallel adder can do? Basically, it is also a combinational logic circuit. For our example here, I should consider a 4-bit parallel adder, because here this parallel adder can do addition between two 4-bit numbers. Let it be my first input is A input, which have a 4 bits A3, A2, A1, A0. And second input is B. Again, it has a 4 inputs B3, B2, B1, B0. It do addition between these two 4-bit numbers. It will produce a 4-bit sum, that is S0, S1, S2, S3, along with a final carry C out. We know that a full adder can do addition between 3 binary bits at a time. This ripple carry adder or a parallel adder we can implement with 4 full adders. By considering this third input initially is equal to 0, and by taking this inputs as it is, whatever the carry it can produce, that should be applied to the next stage. This full adder 1 can do addition between A1, B1 along with a C1. It will produce S1, and also it will produce carry C out. This full adder can do addition between A2, B2 along with a C2. It will produce some output, that is S2, and carry output C3. And this adder can do addition between B3, A3 along with a C3. It will produce some output S3, and carry output is C out. If you observe this case, the carry was propagating from least significant side to most significant side. Because of this, this is we call as ripple carry adder, because your carry was propagates like a ripple from a least significant side to most significant side. The major problem of this particular adder circuit is, in order to do addition between A1 and B1, we should wait to get a C1 from previous adder circuit. Similarly, in order to do addition between B2, A2, I should wait getting of C2 from previous stage. The same thing is applicable for addition between B3 and A3. I have to wait to know the value of C3. And one more interesting thing is, in a least significant side, instead of this full adder, I'll also go and use half adder circuit. We know that a half adder can do addition between 2 bits. That time we are ignoring this C. Directly we are applying A0 as well as D0. This is a 4-bit case. If you extend the same thing to n-bit parallel adder that we designed with n full adder circuits, or 1 half adder and n-1 full adders. For example, here replace n with a 4, because here we are implementing a 4-bit parallel adder. I use 4 full adders, or I can have one more option, that is 1 half adder along with 3 full adders. The major problem of this is I should wait getting of carries from lower adder side if I want to do addition at higher adder ends. That should be the major problem of this. It can be overcome by using another adder called carry look ahead adder. Basically, it is a fast parallel adder. In this adder circuit, what we do is we are going to calculate higher order carries by using a circuit called a carry generator. So by using this carry generator, I'll go and calculate higher order carries by simply taking a full adder circuit. In that case, I'll go and find out what is carry propagate circuit as well as carry generate circuit, right? So see here, friends, So this is, I consider a full adder circuit. So this is a half adder 1, a half adder 2. Here a PI I can call as carry propagate, which is an exclusive OR between AI and BI, and GI is carry generate, which is AI BI. Coming to this second half adder sum output is PI is exclusive ORing with the CI. So what PI is? It is AI is exclusive ORing with the BI, and here carry is CI plus 1. What CI plus 1 is? It is that is nothing but here we are getting PI as well as CI plus GI. This is a GI, this is a PI, and this is CI. So now I have to go and calculate what this CI plus 1 is. So see here, friends. So Boolean functions for C1, C2, C3. Let it be if I assume this I is equal to 0, P naught is equal to A naught is exclusive ORing with the B naught, which is my least significant vector. This is the carry propagate. Carry generate is G naught is equal to A naught, B naught. So C naught is equal to as usual. If I go for C1, then my CI plus 1 expression, CI plus 1, I is equal to 0. Then it is C1. C1 is equal to C naught plus P naught C naught. Similarly, if I is equal to 1, CI plus 1 is equal to CI plus 1 is equal to C2, which is equal to G1 plus P1 C1. Already we know that what a C1 is. C1 is G0 plus P0 C0. That I was substitute here. Then I was getting the C2 value is this. In order to calculate a C3, if I is equal to 2, my C3 is equal to G2 plus P2 C2. So I know the C2 value. Here I substitute that C2 value. Then my C3 value is this. Like this, I'll go and calculate higher order carries only by considering the input values. So that is A0, B0, A1, B1, A2, B2, A3, B3. By considering of these values only, I'll go and calculate what my higher order carries are. So by using these carries, I'll go and design a carry generator circuit. That is this. C0 is an input carry. C1 just I know calculate G0 plus P0 C0. And C2 is equal to G1 plus P1 G0 plus P1 P0 C0. And C3 is G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. See here is, this is a 2 input AND gate. See here, friends, this is a 2 input AND gate. Is ORing with the third input is G0, that is this. So it is C1 is. Then C2 is a G1 plus P1 G0. This is a P1 and this is a G0 input. And this AND gate will produce P1 P0 C0. So this is the C2 is. Similarly, C3 case is, this is the carry generator circuit which can generate higher order carries for me. And next, this is my carry look ahead adder is. This is a carry generator circuit. This is the initial stage of half adders, which are used for generation of my carry propagate outputs as well as carry generate circuits. With the help of them, this carry generator circuit will generate a carries, that is a C1, C2, C3, C4. So with the help of output XOR gates, I'll go and get my sum outputs and a carry generator circuit will produce final carry out. So with the help of this carry generate ahead of my addition, I'll go and carries based on my input values. So what are the disadvantages I was identified in ripple carry adder that can be overcome in this carry look ahead adder is. And next coming to half subtractor. What a half subtractor? It is a combinational logic circuit which can perform a subtraction between two inputs or two binary bits at a time, and it will produce difference and borrow are the outputs. So again, it's a block diagram representation. It have a two inputs and two outputs, and its a truth table is like this. XY are the inputs, 0 minus 0, difference 0 borrow 0, 1 minus 0, difference 1 borrow 0, 1 minus 1, difference 0 borrow 0. Now coming to 0 minus 1, originally this subtraction is not possible. I took a borrow, so borrow is 1. Then here this value changes to 2. 2 minus 1, it is equal to 1. Why here we are getting 2? Because these are the binary values. So borrow is equal to base value of those numbers. So here the numbers are binary. So base value is 2. 2 minus 1 is equal to 1. So the output expressions, again, if you're observing this, x, y along with a difference output, again, it looks like an exclusive OR gate output, right? So that is I written here is D is equal to x, y bar plus x bar y. So this is our logic diagram. Difference can be produced by an XOR gate. But coming to the borrow is 1 for x bar y. So x bar y case, if I consider a minter, so x bar y, that means I need an AND gate. So for that, one input is y directly connected. I need x bar so that it is applied through and not gate. So it will produce as borrow output. Then coming to a full subtractor. What a full subtractor can do? It do the subtraction between 3 binary bits at a time. And again, it will produce 2 outputs. One is a difference and borrow. See here, friends, that is your block diagram representation of full subtractor. It has a 3 inputs and 2 outputs. Coming to the truth table case, 0 minus 0 minus 0, difference 0, borrow 0, 0 minus 0, 0, 0 minus 1. In order to do this subtraction, we need a borrow. So borrow is 1. Then 2 minus 1, difference is 1. Again, 0 minus 1 not possible. Again, I took a borrow. So borrow is 1. Here I was getting 2. 2 minus 1 is 1. 1 minus 0 is equal to 1. Again, 0 minus 1 not possible. Again, I took a borrow. So borrow is 1. Here, the value is changes to 2. 2 minus 1 is 1. Then 1 minus 1 is equal to 0. Next, 1 minus 0 is 1. 1 minus 0 is equal to 1. So difference is 1. Borrow 0. Up to this, 1 minus 0 is 1. 1 minus 1 is 0. So difference 0, borrow 0. 1 minus 1 up to this, difference 0, borrow 0. 0 minus 0. So difference 0, borrow 0. Next, 1 minus 1 up to this, difference 0. Next, 0 minus 1. It is not possible. So we took a borrow. Then it is 2 minus 1. Difference is equal to 1. If you consider a min terms, your difference is 1 for 1, 2, 4, and then 7. I written. And borrow is 1 for 1, 2, 3, and then 7. Like this. Now, if I simplify them by using again K maps, then I was getting an output expressions for a difference is like a sum expression. X is exclusive ORing with, Y is exclusive ORing with Z. Why? Because again here also I was identifying that is isolated terms. But coming to borrow case, here there are 3 pairs are formed. For this pair, the value is YZ, that is this. And for this pair, it is X bar, unchanged value is Z, so X bar Z. For this pair, X value not changes, so X bar, and unchanged value is 1, that is belongs to Y. So these are the expressions, and this is the logic diagram corresponding to it. And next one is a parallel subtractor. It looks like a parallel adder. Parallel adder, what it do is, it will do addition between 2 multi-bit numbers. In a similar way, a parallel subtraction can do subtraction between 2 multi-bit numbers. But here important thing is, this subtractor circuit not designed with the help of parallel subtractors, because the subtraction operation is a little bit complex compared to addition. Because if you have to transfer the borrow from some cases from higher order end to lower order end, it is very difficult process for us. So that what we do is, we do the subtraction with the help of complementations. So this is the subtractor circuit which we are designing by using 2's complement method. In the 2's complement method, what we do is, if I want to do A minus B, I'll go and take a complement for subtrahend B that is added to A. So here I took the 2's complement. So B bar, B is applied through or not again. So here we are getting B0 bar, B1 bar, B2 bar, B3 bar. It is 1's complement of B. And Cn is equal to 1. So that B in plus, the complement of B plus 1, that is equivalent to 2's complement of B. That should be added to A input. So in that process, I was getting the difference outputs as well as carry out. So this is borrow output is. Then in both the cases, one thing is we are using full adders. So instead of using 2 separate circuits, I go with a common circuit which can do both addition as well as subtraction. See here, friends, again I consider only full adder circuits. Again, the C0 is an input carry, and A input in both the cases, addition or subtraction directly applied to full adder. But coming to B input case, it is directly applied for the case of addition, but for subtraction it is applied through a NOT gate. Instead of NOT gate, here I was using an exclusive OR gate. So for exclusive OR gate, one input is B Another input is nothing but M. M is your control input. This M is equal to 0. Then this C0 is equal to 0. This whole circuit should be act as a parallel AND. So it may happen or not. We'll go and check it. So here this input for XOR gate is equal to 0. Another input is nothing but B2. See here, friends, 0 in the sense it is connected to ground. So instead of A, here we have a B. So A is XORing with a 0. Output is A itself. In that process, here the output we are getting B0, B1, B2, and B3. So C0 is 0. So that this circuit will act as simple adder circuit. And next case, if you consider this M bit is equal to 1, that is for subtraction case. Why? Because this C0 initial is equal to 1. And here for XOR gate, one input is equal to 1. It means it is connected to VCC. Another input here is original is B, but here I consider as A. One is exclusive ORing with A. Output is A bar. Means these XOR gates will produce as B0 bar, B1 bar, B2 bar, B3 bar. The time this C0 is equal to 1. That means now your circuit will act as a parallel subtractor circuit. So I hope you understand the adder circuits as well as subtractor circuits. Thank you for patient listening.